Hello, welcome back to the session 8 of module 2. As we have discussed about the ACR different types of modes like forward blocking, forward conduction and reverse blocking mode. We move on further into further different details of an ACR where we are going to see the switching action or the operation of an ACR and of course the commutation circuits of an ACR. That is, the method of turning off an ACR is called as commutation. How we can turn off an ACR using natural commutation or using the forced commutation. And finally, the VI characteristics of an ACR. Hoping to have the concept of an ACR, that the ACR is a 4-layer 3-junction device. As we have seen in this last session, that is, the 4-layer is PNPN and junctions are J1, J2 and J3. And in the 2-transistor model discussed in the previous session, we have already seen how this 2-transistor model of an NPN transistor and a PNP transistor, that 4-layer PNPN, can be splitted up as NPN and PNP. And the connections also we have seen, like how NPN is connected to a PNP to form the complete 2-transistor model of an ACR. Having that concept in mind, the description of the connections I'm not going to tell you once again. Having that concept in the mind, referring to the previous session of the 2-transistor model, we are going to see the switching action of an ACR. In the switching action of an ACR, let a positive voltage V be applied to E1. E1 means let it be anode. And let cathode be E2 here. Okay. And gate G be grounded. Here the gate is be grounded. Okay, be grounded. Both here, this side and this side also we have seen. Okay, as Vg is equal to VBE2 is equal to 0. It means that Vg is 0, VBE2 is 0. Then remember that Vg also is 0, VBE2 also is 0. The transistor T2 is in off state. It means that the collector base here, the collector to base junction of T2 through the emitter base junction of T1, collector base junction of T2 through the emitter base junction of T1 is reverse biased. Therefore, the IB1, the current flowing from the base 1 of transistor T1, the base of a transistor T1 is equal to ICO. ICO is the leakage current due to minority charge carriers. This is too small to turn on T1. Hope it is not confusing. I just repeat it. We have seen in the last session that ACR is a 4-layer 3 junctions. Okay, 4-layer is PNPN, junction J1, J2, J3. Now, having that concept in mind, we are going to see the switching action of an ACR. Let Vg is the gate voltage, anode is E1, cathode is E2. So, as Vg is 0 and VBE2 is 0, if Vg is 0 and VBE2 is 0, this transistor T2 is off. This transistor T2 is in off state. Off state means the collector to base junction of T2 here, the collector to base junction of T2 here, which has been shown here, through the emitter junction of T1 is reverse biased. When it is reverse biased, the base current of T1 transistor IB1 is equal to ICO. ICO means it's the leakage current due to the minority charge carriers. And this leakage current is too small to turn on the SCR, to turn on the transistor T1. Okay, next, thus both T1 and T2 are off, first case, and hence the anode current and IB1 and ICO, that is the leakage current, is very negligible, which means this current is not sufficient to turn on the SCR, and hence SCR is in the off state. That is the switch between the anode and cathode are open, obviously, to tell in simple terms. Now let the voltage Vg is greater than 0 be applied. Vg greater than 0. Here, when voltage Vg is applied, second figure is applied, Vg is applied means greater than 0 at the gate, then as VBE2 here is equal to Vg and Vg is sufficiently large, then VBE2 also will be sufficiently large, and hence T2 will be on. When T2 will turn on, the collector current here IC2 will be large. As IB1, that is the base current of transistor 1, IC2 means collector current of transistor 2. As base current of transistor 1 and collector current of transistor 2 are equal, T1 transistor 1 turns on, causing a large collector current IC1. IA, that is anode current, is equal to the IC1 means collector current of transistor 1 to flow. IA is the anode current is equal to IC1, but the transistor 1 will be turned on and the current will flow. This in turn, what it happens here, what it happens come here. As we tell, this in turn increases IB2, base current of transistor 2, causing a regenerative action to set in. As a result, SCR is turned on. That is the switch between E1 and E2. E1 means anode, E2 means cathode is closed. If the switch is closed between anode and cathode, it forms as a closed switch. If it is a closed switch, the SCR will conduct. The turn on time of an SCR is typically 0.1 to 1 microseconds. For higher devices, for high power devices, then the turn on time may be very high, like 10 to 25 microseconds, like that. So this is the switching action of an SCR. When Vg is equal to 0, how the current doesn't flow and the SCR is in off state. When Vg is applied, how the current flows and SCR is in the on state. Okay, so this is the switching action of an SCR. Knowing the switching action of an SCR now what it is, we are into the state where SCR is completely on state. Now we are going to off. Now, when the SCR is turned on, it cannot be turned off simply at all. Or simply by removing the gate also, it cannot be turned off. Then, what is the mechanism we have to turn off an SCR? That mechanism of turning off an SCR is called as commutation. So, next topic, what we are going in for commutation. The mechanism of turning off an SCR is called as commutation. Once the SCR is on, it cannot be turned off by simply removing the gate signal. Therefore, the two types of commutation has to be implemented, namely natural commutation and forced commutation. In the natural commutation, when the source that feeds the current to the anode of an SCR such that it passes through 0, the SCR turns off at the current 0. That is the case where the SCR is fed from an AC source. This commutation is also called as natural commutation or line commutation. Whereas the other method is the forced commutation. In the forced commutation, we have to force the ACR current to become zero. How we are going to force the ACR current to become zero such that the ACR can be off means the current through the ACR is forced to become zero by passing a current through it, through the ACR in the opposite direction from an independent circuit. A variety of circuits are available for forced commutation, and we can see that forced commutation circuit here. Okay, now what happens next? In the commutation, we are going to turn off an ACR. Next, coming back to the next topic, is the ACR characteristics. That is the VI characteristics of an ACR. We have already seen the ACR characteristics as the three modes of operation. The VI characteristics for different values of gate current is also shown here. Okay, and we have seen that in the ACI characteristics, we have seen that forward blocking region, forward conduction, and reverse blocking, and how the ACR is off or the switch is off in the reverse blocking and forward blocking region because very negligible current is flowing here. So that current is not sufficient to turn on an ACR, and in the forward conduction the switch is being closed and hence the ACR can conduct in this. The current flows. So same as the previously what we have shown for the different regions of operation, the same explanation holds good in the VI characteristics of an ACR also. You can just further scroll up to see the regions of operation explanation so that the same explanation holds good for the, and hence we have already seen about the two terminologies of IL and IH, holding current and latching currents, and how the gate current, whenever it is very close to the anode current, the conduction is minimum and fast. So the same characteristics, the VI characteristics, same explanation holds good as the regions of operation also. You can just scroll back and we can refer it. Okay. Thank you. Hope the session was very good and you have understood it. So, thank you.